Okay, colleagues. So let's start. First of all, I would like to announce the next talk, which will be next week. Jacob Benamonte from Scaltech will introduce his doctoral thesis. It will be about the introduction to modern quantum algorithms, optimization, simulation, and machine learning. So it will be next week. And now our speaker is Peng Xu, and he will talk us about experimental progress towards quantum computing with Rydberg items. Please.
Oh, okay. Thank you, Kerstin. And I'd also like to thank Stas for inviting me to give this talk. It's really a big pressure for me to give a talk online, especially it will be released on YouTube. So I will try my best to not make any mistakes. Otherwise, it's really a awesome thing. So today, I'd like to give the talk about our experiment progress towards quantum computation using Rydberg atoms. Our group, I came from Innovation Academy for Precision Measurement Science and Technology of Chinese Academy of Sciences, which is located in Wuhan. So right now I'm in Wuhan. In this talk, I'd like to first I'd like to show you the background of why we are trying to using neutral atoms, especially Rydberg atoms, for quantum computation, and what is the advantages of our platform compared with other very popular platforms like superconducting systems, like the trapped ion systems. And then I'd like to present two major works, which is of our group, which is done recently in the last 5 years. These two parts, one of the part is a high fidelity single qubit operation. And the other part is what we have realized using Rydberg interactions to construct the heteronuclear CNOT gate. And in the last part, I'd like to give a conclusion and outlook. So I think there's no need for me to give more point about how important is a quantum computation and what quantum computer can do, because there are so many materials and so many news about that. I'd like to start my talk with this quantum computing progress and prospect, which is published by the National Academies of Sciences and Engineering and Medicine. In this report, they have reviewed almost all the platforms for the quantum computer, and especially they give a milestone for quantum computing. In this milestone, they have listed 3 major targets which can be done recently. For the first part, it is a gate-based quantum computer that can demonstrate quantum supremacy with a target to create orders of some 100 qubit gates and qubits, and also to decrease the gate error to better than 0.5%. Also, it is to find some tasks that can computer, but it is difficult for classical computer. And for the second target, which is to implement the quantum error correction to improve the qubit quality. And for the third target, which is very important, I think it is they propose to say that we need to construct a noise intermediate scale quantum computer and find out they can do some useful, they can be commercially useful. And if this target can be done this target should be done in middle or late 2020s. And once this target is finished, I think this will be another milestone for quantum computer. So with the there are so many big corporations, and there are so many countries has devoted so much money on this quantum computing, and there are over 99 organizations working on this quantum computer, on the quantum computation, and this quantum computation is running on 8 different hardwares. We can see from this website, and they're listed right now. There are some adiabatic, superconducting, trapped ion, cold or neutral atoms, or spins, quantum dot, photonics, NV centers, and some topological systems. So from this worksheet, there's one which is indicate we are doing for Wuhan Institute of Physics and Mathematics. They are doing neutral atoms. In fact, this is our institute, but right now we have combined with another institute and form a new academy, which is Innovation Academy for Precision Measurement. So with all these platforms, and we can see the leading platforms are two types, which is trapped ion. For trapped ion system, I think the best one right now is published by IonQ, but Honeywell recently they announced they will publish some quantum volume of 64 quantum computer based on trapped ions in the next month or 3 months later. But until now, I think it is IonQ who are doing the best. Who are doing best in the trapped ion system. They have realized the fidelity for single qubit gate, for 2 qubit gate, and they also demonstrate some benchmark. And for superconducting system, I think most of you may be familiar with that, which is leading by John Martinez in Google, and they have announced they realized the quantum supremacy using a programmable superconducting processor, and they have demonstrated the algorithm that can run in their superconducting chip with some 200 seconds, which will be done in the classical computer with some million years. Although there are some debate about whether they really realize the quantum supremacy, but this one thing there's no doubt, that is they really push the superconducting system quantum computing to a new level, which is indicated by all these parameters with very high fidelity single qubit gate, very high fidelity 2 qubit gate, and they have demonstrated some 1,000 single qubit gate and 100 qubit 2 qubit gate in the quantum chip. So with all this big progress for other platforms, is there any chance for our neutral atom systems? And what is if we look into the quantum computer for further development, is it enough for the current status? So I'd like to cite a conclusion from this report, which indicate what good platforms should be for a quantum computer. That is the key properties to define for a good quantum computer. That should have the error rate, very low error rate of the single qubit gate and 2 qubit gate. And also they should have good interqubit connectivity. And the qubit coherence time should be long enough. Also, the number of qubits should be large enough. So if we judge the platforms from these five directions, and we plot the current status in this radar picture, we can see here. I just give a summarize of the trapped ion system and the superconducting system. From these two figures, we can, or maybe, okay, I should emphasize, this picture may not be accurate. It is just a brief summary due to my knowledge. Okay, and we can see from the trapped ion system, they demonstrate very good coherence time and a very low error rate for the single qubit gate and for the 2 qubit gate, and they can have the 4-int qubit connectivity in a small scale. But the problem is that when the trapped ion system expanded to large scale, to the qubit number of 100 or even 1,000, it will be a problem that the error rate of the qubit gate will decreases. So for the superconducting circuit, we can see even though they have very big progress, the error rate of single qubit gate and 2 qubit gate is not high enough. The error rate is not low enough, and the coherence time is at a medium scale. And the big shortage for this platform is that the interqubit connectivity, it is fixed. So from okay, then I should turn to the neutral atom system. For our neutral atom system, ideally, it should be a very good platform. Why should? The reason is that our neutral atom system is encoded. The qubit for neutral atoms is encoded like the trapped ion system. They all use the electron spin state. So our neutral atom should have very good coherence time, like the trapped ion system. And we should have the error rate for single qubit gate and the 2 qubit gate, like trapped ion system, because we all use laser to manipulate the spin state, to manipulate the qubit. And also for the qubit number, I think it is not a big problem, because people always think about neutral atoms can be scaled to a large scaled to a large number. And what about for the interqubit connectivity? Here there are some proposal for the transfer to have the arbitrary 2 atom interactions. So ideally, neutral atom system is really a good platform. But actually, 5 years or 5 years or 6 years before, our platforms, the neutral atom platforms, is really in an embarrassing situation. We have very high error rate for single qubit gate, and for the 2 qubit gate, we didn't demonstrate the interqubit connectivity, and the coherence time is at the millisecond scale. The only thing is that in the optical lattice, people can have some thousands of atoms. So we can see there's a big gap between the reality and the ideal situation. This reminded me a famous poetry who said, between the ideal and the reality, between the motion and act, for the shadow. So we can see there are so much shadow for our neutral atom systems, and we have to do our best to remove these shadows. And luckily, in the in the last 5 years, for our group have made some progress of these platforms towards the ideal state, and we have constructed the magic intensity trap to extend the coherence time to some 100 milliseconds. That is five scales over the gate operation times. And we also demonstrate we can have a single qubit fidelity with the error rate as low as 10⁻⁴. And we have constructed the heteronuclear 2-atom gate. Although the gate fidelity is not as high as possible, not as high as some 0.9, but it's just a step towards the 2-qubit gate. And we have demonstrated the coherent transfer between the atoms between different sites. So, and especially recently, in the last year or in last year and this year, Michelle Lukin's group and Mark Safman's group, they have improved the 2-qubit gate to 0.9, which is the error rate of 0.01. And recently, I noticed in Eichler Earth system, people have demonstrated the fidelity, 2-qubit gate fidelity of 0.99. So all this progress indicate our neutral atom system is really a very good and have very good potential for the future quantum computer. And so this is a background. Maybe it's a bit long, but in the following part, I'd like to demonstrate how we realize this high fidelity single qubit operation. And before I introduce the qubit operations, I'd like to give a background of how we trap single atoms. We just use a high numerical aperture lens to focus the red detuned laser into a mod. And then due to the collisional blockade, there's only one atom can stay in the trap. We can see from the fluorescence collected from this dipole trap. There is clearly 2 stages. With the lower one, there's no atoms, and with the higher one, there's 1 atom in the trap. So we do our experiment when we see there's 1 atom in the trap. With the atom in the trap, we encoded the qubit with different hyperfine state. Usually we use the magnetic insensitive state, which is MF = 0 state. Here for rubidium-87, we just encoded the 0 and 1 state for yes, F = 1, MF = 0, and F = 2, MF = 0, using optical pumping to pump all the atoms into this state. And then we use microwave or Raman lasers to coherently drive the qubit from 1 to 0 state, between this 0 and 1 state. And if we want to have very high fidelity single qubit operation, the first question is how to benchmark, how to measure this fidelity. There's a standard method, which is randomized benchmarking. The main method is the main idea is when we first initialize the atom in the first state, and then we do a series of operations, and in these operations, the gate errors will accumulate. Then in the state readout part, we use a UR state to map the population into 0 or 1, and then we measure this population then we can infer the fidelity of the operation using this formula. And previously, there are several groups trying to improve the gate fidelity, but they face some problems. The main problem we can see from this sheet is that it is a coherence time. All the experiments come out to a conclusion that the coherence time of the qubit limits the final fidelity for single qubit operation. And the problem is which decreases, which is the main result, which is the main reason to limit the coherence time of a neutral atom qubit in the dipole trap. It is like this because the atom is trapped in the dipole using a dipole laser. The dipole laser is not an infinite detuning. This detuning, if the detuning is not large enough, we can see it will have different trap depths for these two states, which we use to encode the qubit. For the lower state, it will have some potential like this, and in the up state, the potential will have will be different. And the difference is like this. We can see from the AC stack shift, which is inversely proportional to the detuning. And this detuning, if the gap between the qubit state is 6.8 gigahertz, then it will see some difference. And this difference can be as large as to some 7 kilohertz per millikelvin, which means if the trap depth is 1 millikelvin, it will induce the maximum differential light shift to some 7 kilohertz. So how to eliminate this differential light shift? There is one way to do that, using a circular polarized dipole laser with a bias magnetic field to compensate the scalar, to compensate this scalar light shift. And here is our result. We can see when we construct this magic intensity trap, we have extended the coherence time from 1.4 millisecond to some 100 millisecond. And if we add some spin echo to further eliminate some inhomogeneous defacing mechanism, we will have some coherence time to 700 milliseconds. And let's do some simple estimation. If the single qubit gate time is some 100 microsecond, then we have then 100 millisecond coherence time still have the error rate of 10 to minus 4. So can we improve the coherence time? What is the main limit in the magic intensity trap? Here is a table of our decoherence mechanism, and we can see clearly it is a magnetic fluctuation which matters, which limits our coherence time to 300 milliseconds. So we have done a lot of work, some very minor work. We eliminate anything, even the power source, and even some very tiny things to try our best to suppress the background magnetic fluctuation. And also we use some active feedback to compensate the magnetic field fluctuation. And finally, we can have our T2 star coherence time to 600 milliseconds. And the spin echo coherence time can be extended to nearly 2 seconds. In this situation, it is possible to have a single qubit operation, the fidelity better than 4.9. And in this situation, we use the microwave and the randomized benchmarking to calibrate the single qubit operation. And this operation, after many optimization, can be as low as 3 multiplied 10 to minus 5, which means our neutral atom single qubit fidelity is better than 0.49. And here, in our experiment, we can see clearly the gate fidelity is related to the coherence time. With better coherence time, with longer coherence time, we can have better single qubit operation fidelities. And with single qubit operation, it is not enough. It is better to see whether we can have the operations, single qubit operations, in the atom array. In the atom array with more atoms, can we still have each atom with a very high fidelity? Then we just construct this trap array using 2D ALD. With this trap array, we can have single atoms in each trap, and we calibrate one by one, following this route. We can see all these 16 single atoms in the trap site can have similar qubit operation fidelities, which is 10 to minus 4. And all this work is published in PRL in 2018. Here is some preliminary result which we are trying to construct the defect-free single, which we want to construct the defect-free trap array, single atom array. So I will pass it. So in this part, I just show you how we realize this high fidelity single qubit operation. In the next part, I will turn to the heteronuclear CNOT gate.
Excuse me, we have a question from Stanislav.
Mm-hmm.
Yeah, I just wanted to ask, you said that you have implemented some active feedback on the magnetic field to stabilize it. So what was the error signal? So how do you actually implement the feedback?
We use a detector, a magnetic field detector, which is have the sensitivity of 1 milligauss.
So it was outside the chamber, right? So it was not atomic signal. It was just some.
It is located near the chamber, and because the magnetic fluctuation is mainly due to the background. It's all around the environment, and it doesn't matter if you put the detector inside or outside the vacuum chamber, just near the.
Yeah, then you just try to hold like a specific value of the magnetic field on this detector, right? So
Yes.
And the second question is, well, you still have some residual inhomogeneous defacing. So what is the source of this? Is it heating from the laser, or what is? You said that you still have some residual inhomogeneous defacing because
Inhomogeneous. This homogeneous defacing.
Yeah, I mean, because the coherence time in your echo scheme differs from what you see without scheme echo, right?
Yeah.
So there should be some inhomogeneous dephasing.
Yeah, this homogeneous defacing is inhomogeneous defacing. It is a thermal motion.
Yeah, but in the magic intensity, it seems like you eliminate this problem.
Yes, of course. We just eliminate in the. Maybe I didn't show the page here. I didn't show the page here. You can see the magic intensity trap. It is not a flat line. It is not a flat line. It is still it still shows some curve. We just put the. We can see for the first stage of the curve is 0, but if you look it into a larger range and to the second order, it will still show some fluctuations. And
it's still less than the homogeneous dephasing time, right?
Yes, because it is a second order. I think it is a second order dephasing mechanism. And this, you can see here, it is actually it is a competition between this item and this item. And for the magic intensity trap, this item is not as large as this one because the magnetic fluctuation, which actually play an important role here. Because for the magnetic fluctuation, it is the first order.
So we may continue, yeah?
Yes. Yeah, I'd like you to interrupt me at any time and give me some feedback. Otherwise, I will lose my passion to continue my talk. Yeah. So here, the third part is for the heteronuclear CNOT gate. So why we want to construct the heteronuclear CNOT gate? Because it is really matters. If we can see from the trapped ion system. For the trapped ion system, there are also using the heteronuclear setup because they can use one atom for quantum computation and the other atom for sympathetic cooling, or they can use one atom for computation, the other ion for quantum interface. So the similar things is for neutral atom system. If we just use one species of the atoms to do the quantum computation, one major problem is the crosstalk. You can see when we have all the atoms placed nearby, then when you try to manipulate one atom, it is hard. It is very difficult not to. You should be very careful to operate one atoms in order not to affect the nearby one, because the two atoms are very nearby. So, but if we use different atoms arranged far away or just arranged one by one nearby, then we can have some beta. We can have some better performance in this in reduce this crosstalk. And another advantage for the heteronuclear system is we can use one species of the atoms for computation qubit, and the other qubit for measurement. We can have these two species of the qubit executing different tasks and simultaneously. This is important in the near future for quantum error correction, especially for the they have in this paper they have proposed some error correction code using heteronuclear systems. So this is the major motivations for us to do the heteronuclear gate, to construct the heteronuclear system. And for the heteronuclear systems, how can we construct the CNOT gate between two different species? Here we use the Rydberg interactions. First, we use this setup to trap a rubidium-87 in one trap and the rubidium-85 in another trap. We use some technique to make sure that in this trap we have one rubidium-85, and in this trap we have one rubidium-87. With these two different atoms, when we excite the atoms to the Rydberg state, then the dipole-dipole interaction or the van der Waals interaction can have the interactions for these two atoms in a faraway situation. But to excite the atom to the Rydberg state is not an easy task, because we need to because the Rydberg state have long lifetime, which means to excite the atom from ground state to Rydberg state, you need to have a very good laser system. This laser system should have very narrow line width, and also you should have a good power stabilization, and also the straight electric field compensation. Anyway, after our effort, we have realized the coherent excitation between the ground and the Rydberg state with the efficiency over 0.96. And in this case, we can demonstrate the Rydberg blockade between heteronuclear atoms. Here is some demonstration. You can see for rubidium-87, we use it as a control qubit, and for rubidium-85, we use it as a target qubit. When rubidium-87 in the up state, the excitation will not excite the atom to Rydberg state. So 85 will have a good Rabi oscillation between ground and the Rydberg state. But if 87 in the up state, then with this Rydberg excitation laser pulse, it will be excited to the Rydberg state, and then due to the dipole-dipole interaction or van der Waals interaction, 85 will have a shift, and it will have an energy shift, which is proportional to the interaction strength. And due to this energy shift, 85 will no longer have the oscillation between ground and the Rydberg state, which is demonstrated here. You can see almost there's no excitation, there's no Rabi oscillation. With this Rydberg blockade, it is a good mechanism to construct the control gate, to construct the control phase gate, and the control phase gate combined with two single qubit operation, we will have a CNOT gate. So here we have demonstrated the rubidium-87 is a control qubit, and the 85 is a target qubit, which is a tomograph for the heteronuclear CNOT gate. But this fidelity is 0.73. It is a bit, it is not a big deal right now, but at that time, it is still a breakthrough for the heteronucleus systems. And we also measure the entanglement, the parity. We measure the parity of the entanglement to verify that these two atoms are really entangled. This entanglement is constructed like this. We just add a 2 pi powers. We just prepare the control qubit in a superposition state, and then after this CNOT gate, we can construct the entanglement between these two atoms. And then we add some analyze powers to extract the population, and this population see the parity to from this oscillation we can extract the coherence between these two states. So the final fidelity for this two atom entanglement is calibrated to be 0.6 or nearly 0.6. So we are not satisfied with all this readout, although it is published on 2017. So in the later stage, we have make great effort to improve this fidelity, because the target, our target of the CNOT gate is 0.99. So we analyze the fidelity loss for our system. We can see there are majorly 3 different parts. For the first part, it is the background loss, and for the second part, it is due to the Rydberg excitation. And another important one is the random phase accumulate during these 2 pi powers. It is because for this pi excitation, during this time gap, the control atom will accumulate a random phase. So we have do some detailed analysis. If you are not interested, I will pass it. And these single operations, it is some we have improved this background loss to less than 0.6, because in the single qubit operation, we can see it is we can see here the starting point is 0.98. So the background loss is less than 0.02. It's less than 2%. And also there's another fidelity loss due to Rydberg excitation. We can see from this figure, it is not down to 0. This peak is not down to 0, and the atom loss is is about 8%. So even after we subtract the detection error, the Rydberg excitation efficiency is still not as high as 100%. And also there's some strange pi Rydberg pulse, which is first reported by Mark Sufferman. And we also observed some similar problems in our setup. But later, it is realized that this Rydberg excitation loss is due to the laser phase noise. And this laser phase noise is because when we try to suppress the line width of the excitation laser using a high finesse cavity, we can see some servo bump here. The servo bump, this servo bump has a frequency range very close to our excitation period. So it really matters. And it is first pointed out by Michel Lukin's group. And in our setup, we use this high finesse cavity to use the transmitted laser and then injection to eliminate this phase noise. And here we can see we really have a better result that is 3 orders better than before for the phase noise, for the laser phase noise. And here is our result. We can see at this time we can have better readable the Rydberg excitation. And this Rydberg excitation, when we do the gap pi excitation, there's almost no loss here. And for the fidelity loss due to random phase, we're also doing an experiment to verify this effort. Because as you can see, the control qubit suffers Rydberg pi pulse and then de-excited from Rydberg state. But since the control qubit is in a superposition state, and after the first pi pulse, the control atom will be prepared in a superposition state of the ground and the Rydberg state. And this superposition state is very sensitive to the electromagnetic field and the electric field and the background electric field, and also any effort that induce the energy shift of the Rydberg state. So it is very fragile. And we do an experiment, and we have done an experiment to verify this and do some simulation. We get an empirical formula that when the atom temperature is very high, when we use this pi gap pi pulse, when we use this pi gap pi sequence, we will have a gate error, which is proportional to 0.836 multiplied by this. So how to suppress this random phase induced fidelity loss? This is one way. If you can reduce the atom temperature to a very low level, then it's okay. But we have found out another way. Recently, we proposed in physical review apply off-resonant modulated driving method. For this method, the main idea is like this. We can see here, if one atom in upstate and the other, if the 2 atoms in 1 zero state, it will, there's only 1 atom doing Rydberg excitation. But if the 2 atoms are in the same state, due to the Rydberg blockade, the Rabi oscillation will have square root of 2 divided by 2 amplify. So for these 2 states, they will have different Rabi oscillation. They will have different Rabi frequency. And maybe for this, maybe we can design some spatial evolution route that fulfill after this pulse, the population will return, but the phase changes for this state. The phase doesn't change for these 2 states, but for the 0 state, it will have a pi phase shift. This is corresponding to the controlled phase gate. Following this route, we just modulate the amplitude of the laser pulse, and we find out it is possible to realize a very high fidelity controlled phase gate. this fidelity can be as high as 3.9, and here it is a simulated readout. And more importantly is that because it is an off-resonant drive, the atom will not populated in Rydberg state. So the random phase accumulated in Rydberg state will be very small. And this protocol is very robust. It can have it can endure the effective detuning as large as some 100 kilohertz. And also, if the driving laser is not balanced, which means for atom 1, the Rabi oscillation is 1, and for another atom, the Rabi oscillation is 0.99. It's okay. They still have a very high fidelity. So here we recently published this result.
May I?
Yes.
So
Yep.
why is there so the detuning dependence? I think it's what is plotted there. It's the error versus the effective detuning, or what is that?
For this figure?
Yes, this one. Why it has a minimum there? Because
this is on resonance.
This is on resonance.
This is on resonance. This is on resonance because you see it is for some -3 megahertz because you need to compensate for the edge stack shift of the 7-8 nanometer laser.
Okay, I see. So this the and what is the actual detuning of the Rydberg lasers for this off-resonant protocol which you simulate? How large is the detuning of the excitation lasers? Oh, you said that it's an off-resonance, so how far off resonance should you be?
Megahertz is enough. So recently we are doing this experiment. We are trying to realize this. This is what I showed you last year, but so we want to use this protocol to have a high fidelity controlled phase gate. Yeah. So another interesting thing is we have balanced the coherence time of these two qubit gate. Of these two qubit, because for this heteronuclear system, we have rubidium-87 and rubidium-85, but the coherence time is quite different. So we just tuning the magic intensity, the circularity of the magic intensity trap to compensate the difference between rubidium-87 and rubidium-85. So finally, we can have rubidium-87, the coherence time about 1 second, and rubidium-85 also have the similar coherence time. This coherence time balance is really important for the later stage, because when we construct the CNOT gate between these two atoms, and if one of them have lower coherence time, it will limit the total coherence time of this entangled system. And this result is also recently published. So, okay, I think I almost finished my talk. And here I come to my conclusion and outlook. Yeah, so I will come back to this radar picture and to see what we have done and what we will do next. And we can see clearly we have some shortage which is for the for the high fidelity 2-qubit gate and the qubit numbers. So right now we are trying. In our setups, our target, our main task is to improve the fidelity of the 2-qubit gate, and also we construct a new setup for the defect-free atom array. And in the later stage, we will try to find some unique advantages for neutral atom quantum systems, because to demonstrate some unique advantages, like the larger numbers of atomic qubits, like the to have the uniformity of the qubit operations, and also to demonstrate some multi-qubit gate. Especially, it is possible to demonstrate some 3D surface code, although it's difficult, but we will think about it. And for the Misc architecture, I think for neutral atom system, there are almost the same as other apparatus. I think they will be divided into all these different parts, from some physical system of qubits to the analog and the digital devices to control the qubits, and also the microarchitectures, some quantum instruction set. So I think there are so many there are many companies already doing this, like a quantum compiler, like the quantum instruction set and the QStick. They already have some commercial softwares. Yes, I think I finished all my talk here, and yeah, I'd like to thank my foundings. Yeah, that's all. Thank you.
Thank you so much. So please, questions.
I think Paula has a question.
Xiaoson, please.
Okay. Thank you, Peng, for this very nice, very interesting talk. And I have some questions regarding to the second part of your talk about first question is about this two-dimensional trap array. And in order to perform efficient quantum computation, do you need to have nearest neighbor interaction, or just the nearest neighbor interaction is enough for you?
Yeah, it's really a good question. Actually, if you have very high fidelity 2-qubit gate, then the nearest neighbor interaction is enough, because in principle you can always transfer the interactions using a series of 2-qubit gate from one atom to another atom. That's enough. That's in principle it's okay. But actually, if you do a series of CNOT gate, you need to have very high fidelity gate. Otherwise, the fidelity will decrease very quickly. And also, it is time consuming to use a series of CNOT gate to transfer the interaction from one position to another position. So this is one point. In principle, it is okay, but actually, it's better to have some longer range interactions.
Mm.
Yeah. So for our neutral atom systems, the Rydberg interaction can cover the interaction range that is as large as some 10 or 20 micrometers, which means it will cover some. If the atom is in the center, it will cover some 4 multiplied by 4 atoms nearby.
Right. That's very exciting, and that's the advantage of using Rydberg atoms, I believe.
Yes.
Because the size of the orbital is just much larger than the like the usual atom size. Yeah.
Yes.
Mm-hmm. At the end of your talk, you talk about 3D surface code. Can I imagine that the 3D surface code map into a 3D trap, 3D dipole trap?
Yeah. It is I think this is really a unique advantages for neutral atom system, because to my knowledge, the only possible platforms to construct the 3D constructions, to construct the 3D pattern, is only the only platforms is neutral atom systems. It's for neutral, for dipole trap. In France, Anton Breuer, they have demonstrated the 3D pattern of the atom array.
That was realized by, for example, probably by spatial light modulator.
Spatial light modulator, yeah, spatial light modulator. Yeah, using spatial light modulator to construct the 3D trap array, and then move the atoms in each plane, and then one by one to construct the defect-free 3D atom array.
Yeah, that's definitely. That's I believe that was the dream of the optical lattice community at the beginning of 2000. They want to build such thing. Yeah. So one last question is about the feedback, the magnetic feedback you talked in the first part of the talk. So how sensitive, like what kind of sensitivity of your arrow signal from your Gauss meter, I believe, and what kind of feedback, and what kind of feedback loop bandwidth you required for this compensation?
Yeah. Actually, the arrow signal, we use the Gauss detector with a sensitivity of 0.1 milligauss. And it is, we have the feedback loop at the bandwidth for the feedback loop at a very, some 100 hertz. Because it is not very fast. It is very slow. We just want to compensate the drift.
Okay. Okay. Yeah. Thank you.
You're welcome.
Okay. Any other questions? Paolo?
So thank you. Very nice talk. It's very nice to see that there are some other possibilities besides superconducting stuff and ions, trapped ions, and so on. And so my question is more or less in the same lines of the question Xiao Song asked first. So far you have addressed the atoms by frequency tuning. Is that correct?
Yes.
So, but then if you want to increase the number of atoms for computation, so you would need to address them spatially. So you would need to have some spatial resolution, right?
Yes.
So, so far you are not doing this, but there are some possible strategies. Could you please tell us a bit more how to deal with this problem?
The addressability, the single atom addressing is really a hard task. Yeah, this is a very crucial question. Yes, this question is very good. And right now, people usually just still using some focused laser. a focused laser, trying that is they're trying to find some balance between the crosstalk and the addressability, because when you use some small addressing laser, which means the operation fidelity will decreases, which is limited by the atom temperature. But if in the later stage, when people are using Raman sideband cooling to cool all the atoms down to the ground state, then it's okay. But right now, we still need to find some balance between this, between the addressability and the crosstalk. And when the addressing laser is too small, it will decrease the operation fidelity. When it is large, it will affect the nearby atoms. So in the future, so people make some balance in the experiment. And in the later stage, I think in the future, a Raman sideband cooling to cool all the atoms down to the ground state is the best way. In that case, when the addressing laser is still small, then we still can have a high operation fidelities. And I think it is to decrease the temperature of the atoms, either by Raman sideband cooling or EIT cooling or some other ways.
Okay, so one more. I have another question. I don't know. You're probably not concerned with this problem, but your system and the level of control that you have on it, it looks suitable for studying quantum thermalization. Have you ever thought about this in the system?
Pardon?
Your system seems suitable for studying quantum thermalization, meaning that you prepare these atoms in an initial state, and then you let them interact between themselves, and they evolve to some stationary state, and then people try to understand how this evolution to some equilibrium state is related to some thermodynamics parameters. So I see that it's not your focus, but I've seen some people using this kind of system for studying this problem. Did you think about something related to this?
I don't think about it because there are so many difficult tasks waiting to be solved in my setup for quantum computation. So I don't have too much energy, too much time to do this quantum simulation work. But I think the best work is done by immune block. They are using Rydberg addressing, in the optical lattice, then to induce the interaction between them and to watch the involve to reach equilibrium. How to spell that? It's really hard for me.
Okay, so thank you very much.
You're welcome. You're welcome.
Okay, Ranjit, please.
Thank you for your talk. I have two questions. First one is, what is the range of optical pumping frequencies you use for doing gate operations?
Optical pumping. The frequency range for optical pumping. You mean here, optical pumping? Or
yes. Yes.
Here, I use rubidium-87, which is for pumping. For this is the pumping laser. and combined with some repumping laser. And this pumping laser, I used D1 line, that is 795 nanometer. And for this repumping laser, I use D2 line, which is 780 nanometer.
Okay, thank you. Second question, do you have a radar chart for photonic hardware platform? Because I have seen other radar charts, but I have not seen for photonic hardware platform.
Sorry, could you repeat it again?
Yes, in your presentation, I think it was maybe third or fourth slide where you are showing or spider chart or radar chart. So there is a graphical picture.
This one?
Not this one. I think 40th slide, 40. So do you have similar picture for photonic hardware platform?
No, I don't have. I don't have a similar picture for hardware, for photonic system.
Okay, thank you.
This is drawn by myself, and so maybe there are some problems, but I think it is, to my knowledge, it is the best for me.
Thank you.
Okay, thank you. Any other questions, please?
Well, I may ask a couple of
technical
questions if there's no. So the first one will be about slide number 38, I think.
38, this one?
Yeah, this one. So you said that you tune the magic, the position of this magic point by tuning the ellipticity, right? So it's not circular anymore, but elliptical.
Yes.
And well, do you see any reduction in the lifetime in the elliptically polarized trap?
No.
Or
no. As long as you do not add some resonant light during this elliptic trap, you will not have any reduction in the lifetime. The major point is the resonant light.
Yeah, see, because well, I've seen some works where there was a strong dependence of the lifetime of trapped atoms on the ellipticity. It was like the largest lifetime for perfectly linear and perfectly circular trap, and for all elliptical state was reduced by like an order of magnitude almost, I think. And the explanation was that there are some transitions between different Zeeman states which are coupled to the motion of the atom in this elliptically polarized traps, something like that.
Maybe you can share the paper with me.
Yeah, I can share the paper with you, but you haven't seen anything like that. Yeah? So it leaves perfectly well independent of the polarization.
Because you can see the coherence time is
if the lifetime was reduced, yes, we will not see like a second. Okay, that's interesting.
So, any other questions? Okay, if that's all, thank you very much. Let's thank the speaker and see you all next week at our next seminar. Thank you.
Thank you.
Hey,
Thank you all.
Bye.
This nice talk.
Good to see you.
Yeah, nice to meet you.
Good luck in your work. Very nice stuff.
Thank you.
Pleased to see you. Bye-bye.
Bye-bye.
I know.
Stas, maybe we can use this room, or we just move to another room.
Yeah, I think we can move to another room if you want to discuss. Right. I will send you.
Okay.
Link,
so I finished this conference. Just send me your slides, please.
Okay.
So see you.
So Peng, I will send you the